Nodal analysis is a circuit analysis technique that is super systematic. It results in specific voltages on the circuit that we can use to figure out everything else about the circuit. It's one of the most powerful circuit analysis technique, and I typically find it my go-to method because of its simplicity once you get a hang of how to do it. So before I delve into how we do circuit analysis, what I want to do is I want to show you the result of this analysis. So in here, we have a circuit diagram, and that circuit diagram has a bunch of elements and a source. And in that circuit diagram, we performed nodal analysis, and nodal analysis resulted in a few voltages. So this voltage and this voltage. So these voltages, VA is 3 volts and VB is 1.5 volts. And typically in nodal analysis, you will see some sort of a reference point somewhere. That reference point is what we sometimes refer to as a ground, or maybe the 0 volt point. Remember, voltage is typically a difference between the potential between two different points. So if we assume that this point is at 0, that means I'm saying that VA, which is here, and I'm just going to highlight it, this is plus, this is minus, is basically I'm saying this is 3 volts above the reference node. Similarly, we're saying that this here is a positive, this one here is a negative. That means I'm saying that this particular point is 1.5 volts above the 0 point. So circuit analysis or nodal analysis will typically result in these two voltages. What I want to show you in here is that we can use just these two voltages to figure anything you want about this circuit. So what I'll do now is I'll go and highlight certain voltages or the voltages and currents flowing through the different resistors on this circuit. So if I assume that this is here is a plus, this is here is a minus, and I said that this here is V1 and the current here is I1, maybe I can also say, well, this here, the voltage between the 3 kilo ohm this is a V2, and I'll assume that the current flowing through it is I2. And of course, I can just say basically this is plus, this is minus. I can call it V3, but this is really VA. It's the same VA because this is the positive point, this is the negative point. That's what the this is basically 3 volts. But anyway, we can do that, and then we can say that, well, the current flowing through that 6 ohms is I3. And then we can say, well, the plus and minus in here, this is basically VB. It's the same point because this reference point is also in here. So this is the negative, this is the positive. So what I'm saying is this particular voltage is 1.5 volts. All right, if I assume that the current going through this one here is I4, and then of course we can also say, well, the voltage across this resistor is pretty much VB actually, because I can say plus and minus, this is VB, because if you think about it, this is the same point in here, and this point in here is the same point in here. So that's also the 1.5 volts. But also we can identify the I5, this is the current. And just a quick comment about how I decided the voltages and the current directions or polarities. So I assume the voltages most of the time, if I know it, I just put it. For example, I know that this is VB, I know this is VB. If I don't know it, I just assume that, for example, here this is V2, this one is V1. And when I went to assign the currents, I made sure that all the currents are hitting the positive. So in here, it's hitting the positive. In here, it's hitting the positive. In here, it's hitting the positive. This one is hitting the positive. And also this one is hitting the positive. And my rationale is when I'm dealing with passive sign convention, I will not have to put negatives everywhere. Anyway, so we have all of this now. That's good. So let's go around and see what we can figure out. So I'm going to start with the voltages across the circuit. So I pretty much have all the voltages except V1 and V2. I have VA, it's here, and I have VB and VB because they're here. So my task now is to figure out what V1 and V2, and I'll be able, basically, I figured out all the voltages across the circuit. So let me show you here. So we're focused first on this particular this particular part of the circuit. So I'm going to just redraw it in here just for ours, so we can track it. So we're going to say that this one here is 9 kilo ohms, and this one here is, well, I don't care how many kilo ohms. What I care about is this. There's some sort of a voltage in here. Of course, I can redraw it. That's okay. Of course, just remember this is part of a circuit. It's not all of the circuit. Okay, so this one here is VA. This one here, we decided that this is V1, and we know that this is the I1. So what we can do to figure out what V1 is of course we can write KVL equation in here. So the KVL equation we can write here, and we say this is the loop. Let's write KVL. So based on KVL, we'll have the negative 12 volts from the source, plus V1 that we're looking for, plus VA, which we know already is 0. So negative 12 plus V1, well, we know that VA is 3 volts equals 0. That tells me that V1 is simply 12 minus 3, which is just simply 9 volts. Okay. Well, this is one way to figure out this voltage, but what I want to do is I want to show you that there are also other ways to think about this voltage. Of course, we can write KVLs everywhere, but if we're doing nodal analysis, chances are you don't want to do that. There are simpler methods. They're basically, we're going to end up in the same result. It's just there's a pattern that you can follow. So let me show you a couple of these patterns. So the first one we're going to do is the following. So I'm going to put it in red. So we can say that this is a node and this is basically another node. And what we can say is really V1 is the difference between these two nodes. So let's assume that this here, I'm going to call it VS. And this one here, we called it VA anyway. All right, so what this tells me is, this is method 2. Let me just do that here, method 2. Okay, so in method 2, it tells me that the V1 I'm looking for is pretty much VS, okay, minus 0, because remember, this voltage in here is pretty much, I'm saying this is the voltage against the reference node in here. So let me just highlight the reference. So we can say that this is the reference in here. Sometimes we do it that way. Sometimes like the reference can be just a flip rectangle or just this few lines as the ground. But anyway, I usually write it this way because it's just faster. So back to the point. The point is in here for V1 is basically the voltage between here and the voltage between here. So the voltage at the first point is actually Vs minus 0 because I know that this is my 0 point. And negative, what I have the second point in here is that, which is basically VA minus the 0 point, okay? And if you just clean this up a little bit, you will see that this is simply VS minus VA. Okay, so this is VS minus VA. Well, we know that VS is 12 volts. We know that VA is 3. That means this is 9 volts, and we got to the same number in here. Okay, this is the same number as that. It's actually the same voltage. It's the same, pretty much it's the same voltage method. You just write KVL in here. The other one, it's like we did a little bit different. But anyway, typically what we have in when we have node voltage, what we have is like, okay, you need V1. Well, just take the voltage in here minus the voltage in here. You don't have to put the negative 0 and the negative 0. So what I want to show you is the following. You will see it, and I'll just basically write it in green in here, that in method 3, and that's basically what we typically do in nodal analysis. So we'll say, well, you need V1. Okay, here's V1. Well, V1 is simply 12 minus the VA, because if you think about this one here, the following, you see that? So we have, it's this point, and I know that this point versus the ground is 12 volts higher, minus this point here, which is 3. So this is what I'm saying, it's 12 minus VA. That's what we typically say, and that will give us, it is 12 minus 3, which is the 9 volts, okay? All right, perfect. So we figured out what the voltage one is. I just showed you several methods, but really the method you should pay attention to is just that third method. So if you're interested in a voltage V1, all you have to do is just tell me it's the voltage in here, whatever value you get, minus the voltage in here, whatever value you can get, and both of the point voltages are against the reference. Okay, so let's apply this analysis to V2. V2 is pretty much the same, so I'm actually asking what's the difference in voltage between this point and this point. Well, you can simply say that V2 is VA, because I'm assuming the positive in here, okay, minus VB. Okay, so let me just write that down. Okay, so we're saying that V2, okay, is just simply VA minus VB. VA minus VB. And that's basically 3 minus 1.5, which is 1.5 volts. And that's it. We know all the voltages across the circuit. So if I actually write these down in here, you will see we figured out that this one here is simply 9 volts. And this voltage is simply 1.5 volts. So what I have showed you just now, that nodal analysis resulted in 2 voltages in here and in here. And these 2 voltages allowed us to compute any other voltages in the circuit. And similarly, we can figure out all the currents throughout the circuit just using Ohm's law. If I know all the voltages and I know all the values of the resistors, we can figure out all the currents. And just as a quick reminder, we know that Ohm's law tells me V equals I times R. That means that I is just simply V divided by R. Of course, we have to figure out what the passive sign convention, whether it's positive or negative. But the way I assumed all the currents across the circuit in here, just as I mentioned before, they're all positive. So if you want I1, let's just write them in here. So let's assume that we wanted I1. So I1 is simply V1 divided by R1. Well, what is the value of R1? I'll just zoom out in here. Or I'll just copy the image and just put it down so that I don't have to scroll up and down. All right, so I went ahead and copied it, just easier. that way. So what we have is we have I1 is just simply V1 divided by the 9. This comes from here. Okay, I know the V1 and I know the 9. Well, I know that simply V1 happened to be 9 volts because it's 12 minus 3. So it's 9 divided by 9, and that's simply 1 milliamp. Okay, and we can figure out the I2. Where is I2? Well, I2 is here, is just simply V2 divided by 3 kilo ohms, and I know that this is 1.5 divided by 3 kilo ohms, which equals to half a milliamp. All right, well, you can figure out the rest as well. I3 is simply, and you can take a look at it, it's here, it's actually VA, which is 3 divided by 6 kilo ohms, which is also half milliamp. Okay, and we have I4, and the I4 is just here, and that's basically VB, which I know it's 1.5 divided by 4 kilo ohms, and that equals to 0.375 milliamp. And finally, I5 is just simply VB, which is 1.5 divided by 12, and that equals to 125 milliamp. And I think that should be 375 milliamps, not 0.375. And of course, the final current, you might be interested in the current going through the 12 volts. Well, it is the same current as I1's,